STM32 is probably the most well-known 32-bit microcontroller out there. And I'd say it's definitely a good starting point when you're first learning about 32-bit microcontrollers. It is, however, a huge jump in complexity over something like a PIC or an AVR. I mean, just take a look at its datasheet. It's over 900 pages long. And that's why I've made this video. I want to help you make the jump from 8-bit to 32-bit. So, without further ado, let's dive in. Just a quick note before this video starts. This isn't a video made for complete beginners. I'll go ahead and assume that you have at least a basic understanding of C code, pointers, memory addresses, and microcontrollers in general. Before we can start programming in STM32, we first have to pick one. There are several boards that you can find on places like Amazon or eBay. For example, you could pick up one of these blue pill boards. They come with all of the required circuitry, and all you need to do is program them. You could also decide to make a board of your own for testing, which is what I did. This is a bit more challenging, however. The specific microcontroller that I ended up using was the STM32L011F4U. It's a Cortex M0 Plus, which makes it suitable for low power applications. It also comes with 16 kilobytes of flash, 2 kilobytes of SRAM. You can also clock the CPU all the way up to 32 MHz. And, of course, it comes with a selection of peripherals, including, but not limited to, a 12-bit ADC, a UART, an SPI, an I2C, and 7 timers. In all, it's nothing too crazy, and everything should at least be somewhat familiar considering that you have previous microcontroller experience. Here's the schematic that I ended up using for my testing board. Your reset pin should be pulled up to prevent unintentional resets. Likewise, your boot 0 pin should be pulled down to ground to boot from flash in the case that you need it. You can optionally add a crystal if you need one. And that's just about it for the bare minimum circuitry. But we need just a little bit more to make it useful. I went ahead and added an FTDI chip to the circuit. This allows us to have a serial interface with STM32 over USB. This can make debugging easier. I also added a 1.8 volt regulator to the STM32. For this specific chip, you can choose any power voltage from 1.65 volts to 3.6 volts. And just one more thing, I added a programming header. This header aligns with the official STM32 ST-Link, which will communicate over SWD. Speaking of programmers, aside from the official programmer, you can get some cheap ST-Link clones. They usually come in this smaller package, so use one of them if you'd like, but I'll stick with the official programmer for ease of use. And in case you were curious of how I soldered everything together, I used a stencil and some solder paste to apply solder. I then placed the components on top and activated the solder by using a hot plate. Anyways, with the construction complete, we are now ready to start programming and testing this thing. The official programming method is to simply use the STM32 Cube IDE, along with HAL. However, for this video, I'd like to explore a more fundamental approach. That should help you understand the STM32 at a much deeper level. For this, you can download the GNU ARM toolchain on this website. The link will be in the description. Alternatively, if you're using Linux, you may download it using your package manager. For example, on Arch Linux, it's called ARM None IABI GCC. Go ahead and get the libnu and GDB packages as well. For Windows, go to this website where you can download the ARM GNU package. Simply run the installer and you should be good to go. You may also opt to download a program that can run makefiles, but this is kind of annoying and you can consider it optional. Now we need a programmer to send our compiled code over to the ST-Link. You could use something like OpenOCD for this purpose. For the programmer though, I simply went with the official STM32 programmer tool. The link for this will also be in the description. With all of the software prepared, we can start working on making Blink. Now, at this point, you may be expecting to just be able to jump into your new main.c file and write to a few GPIO registers to blink an LED, as you might with an AVR microcontroller. However, there is actually a lot more setup that you need to complete first. Let's start with a linker file. A linker file's purpose is to lay out where the compiled data will go into the memory of the microcontroller. AVRs have these as well, but they are pre-made for you. Since we are doing this manually, we will have to make one for ourselves. The first thing that you need to do is to go to the reference manual for your specific microcontroller. Since I'm using the STM32 L011, I'll go to the STM32 L0x1 reference manual. Included is a memory map. This shows us which addresses correspond to the RAM, the flash, and the peripherals. For example, the flash memory starts at address hex 8000000, and the SRAM starts at address hex 20000000. So let's put this into a new file. I'm calling my linker file, for this case, linker.ld. Start by declaring the memory locations that we just found inside of the memory header. The origin keyword is the starting address that we just found, and the length is how large the flash and RAM are. The parentheses around the letters represent the permissions of this memory. For example, R means read, X means execute, and W means write. So, this means that we can read and execute from flash, but not write to it, while the microcontroller is in normal operation. The next line that you should add is this entry line. This tells us the name of the function that our program will start with. You can choose any name that you'd like since you were going to create this function yourself. I'd encourage you to name it reset though, since there are some setup code that we need to run before the main program starts. We will write this reset function later, just keep it in the back of your mind for now. Now we can finally get to the hard part of the linker file, the section header. Basically, when your code is compiled, it's divided and then sorted into a few different sections, including ISR vector, text, RO data, data, and BSS. Starting with ISR vector, this section is our interrupt table. This is a list of memory addresses that point to functions. Each entry in the list corresponds to a specific interrupt. We create this subheader to represent our ISR vector. Inside, we specify that all entries with the .isr vector should be included in this section. We end the subheader with a placement in flash. It's very important to place the .isr vector first, since it should be the first data in the flash. The next section that we have to place is the .text section. This is where your executable code will be stored. We use the asterisk in the second entry to ensure that all sections with .text in the name are included. Again, place this in flash, since we don't want to change any of our code during runtime. The next section that we have to deal with is .ro data. It's basically all of your read-only variables that you include. Again, place this in flash, since we don't want to write to any of them. The next section is a bit more interesting though. The .data section is all of your initialized data that will be changed during runtime. For example, if you were to write int x equals 5 in your C code, it will store a value of 5 so that our code can use the initial value when it does start up. Basically, we need to save this data in the flash, but place it into RAM when we are initializing the variable. We can do this with this line. This basically tells the program that the data will be found in RAM during runtime, but before we can find it, we have to load it from flash first. You may have also noticed the other lines, like the data RAM start line. These function as variables that we can use in our C code. The period in this case represents the linker's current memory location. So we can use these to tell our C code where the data starts and ends inside of the RAM. We can also use the load ADDR to tell the C code where the data is saved and flashed so that we can transfer it over to RAM. We will write the code for this transfer in a bit. And finally, we have the BSS section. This section is simply the variables that should be initialized to 0. We will use these BSS start and BSS end variables to zero out the variables later on. Place this section in RAM. Now that our linker file is completed, we can start writing some setup code. We now have to write some code that will set up the sections that we just created in our linker file. First, make a new C file, I called mine vectortable.c, and create some useful definitions inside of it. The table size definition is how many interrupt entries are in the interrupt vector table. The reference manual has a list of interrupt and exception vectors. Please note that some of the blank spaces in the exceptions take up multiple spots. An easy way to find the number of spaces that you need is to look at the address column. Look at the address of the last entry. Divide this number by 4 and add 1 to get the total number of entries that you will need to account for. For the STM32L011, that's 46 entries in decimal. The next definition is RAM start. We've already found this earlier. And finally, we have RAM size. Since our microcontroller has 2 kilobytes of RAM, I put that number in as the number of bytes. We can finally start writing our next function that we mentioned earlier in the linker script. We have to do a few things. First, we need to copy the .data section from flash to RAM. Next, we need to zero out the .bss section in the RAM. And finally, we enter our main function to get the program started. To do this, create our void reset function. Also grab the linker variables that we made earlier. Use the xturn keyword to let the compiler know that the data is found elsewhere. Now we can copy over the .data section. I find it easiest at this point to convert the memory addresses given by the linker and to turn them into pointer variables. From here, we can simply use a for loop to copy the data over. We use a very similar process on the BSS section, but instead of copying data, we just set it to 0. We can finally enter main. I'd recommend that you add an infinite while loop in the case that you somehow exit your main function, just as a safety measure. We aren't done with this file yet though. We still need to set up our interrupt table. Create a default handler method. I don't imagine that you would have every interrupt planned out, so we will use this handler in the case that you somehow accidentally call an unimplemented interrupt. Next, create a list of every interrupt. The names of all these can be found in the interrupt table. Place an attribute with a weak alias to default handler. This essentially means that if you don't implement a specific handler, it will act as a default handler. But if you later on write that specific handler, it will automatically overwrite that handler instead. It's just an easy way to keep things organized. I'd also recommend placing them in a header file so that you can overwrite them in your main.c file. Now you just need to organize your vector table. You should create an array for this purpose. Include the standard int header so that we can access the uint32t keyboard. Uint32t is another way of saying an unsigned 32-bit integer. Also, give your array the section .isrvector attribute. This will let the linker know that this is the vector table specifically. Anyways, the very first entry in the table isn't actually an interrupt vector, but rather the initial stack pointer. This should always point to the very top of RAM. So to get this, you can simply add the RAM start and the RAM size definitions together to get the proper value. After this, you can follow the reference manual's guide to get the right order. Pay attention to the reserved spaces. Some of them take up several spots. You can go to the programming manual, which is a different document, to get the right number of reserved spaces. And when you do need to fill in a reserved spot, just place a 0. And with that complete, we can finally get to our main function. Let's start writing our main function. We need to set up our output pin and then toggle it in an infinite loop. We would do that by manipulating the GPIO registers, but we don't have them defined yet. At this point, I created an STM32.h header file along with an STM32L011F4.h header file. Anyways, in the header, I've added this macro, reg_pointer32. This will make it much easier to modify the registers in our code later on. I'm basically aiming for a code style similar to the way that I write for AVRs. I've also added a 16-bit version of the macro as well, just in case. Now we can start sorting out where exactly the GPIO registers are located in the memory. If we take a look at the memory map, we can see the peripheral section, and it is divided up into the AHB, the APB1, APB2, and I/O port. I recommend that you define each of these at the top of your header. I also recommend that you define Cortex M0 Plus peripherals, since it will be useful for setting up interrupts later on. Now, at this point, you may be expecting to jump straight into the I/O port registers. But there's still one more thing we need to do. Every peripheral in the STM32 has to have their clock enabled for proper operation. To activate the clocks of other peripherals, you need to take a look at the RCC peripheral. It contains clock settings for the microcontroller in general, and also the individual peripherals. To access the RCC registers, you first need to find its base address. You can find it on this peripheral register boundary address table. As you can see, the RCC is located at hex 1000 from the start of the AHB. Now we can go to the RCC register descriptions. You'll find that each of the registers has this offset value. We can use it in the same way that we did for the RCC to easily assign addresses. For example, the RCC clock control register is at offset 0 from the RCC, so we can just add 0 to it to get the proper memory address. At this point, since we are now dealing with the actual registers, use that reg pointer 32 macro that we made earlier. This will allow you to access the register in your code as if it was another variable. I also recommend going through and making a definition for all of the bits in that register. For example, PLL ready is bit 25, so I defined it as 25. Do the same process for a few more registers. I made one for the configuration registers at offset 0C, the GPIO clock enable register at offset 2C, the APB1 peripheral clock enable register at offset 38, and the APB2 peripheral clock enable register at offset 34, along with defining the pins used in each of those registers. It's worth noting that I did not make a definition for every RCC register, since I won't need many of them. But if you do need the others, just follow the pattern and make a new definition. Anyway, you may have noticed that I included the GPIO clock enable register in that list. And it's the register that we still use to enable the clock to our GPIO. I'm planning on running blink on PA1, so we will have to enable the clock for GPIO-A. Now we can finally get around to manipulating the GPIO register. If we go back to the boundary addresses, we will see that GPIO-A is placed at offset 0 from I/O port. At this point, I recommend going through and defining all the registers with their offsets. The ones that you should focus on are motor, ODR, AFRL, and AFRH. Keep in mind that the X means that it goes for the other GPIO peripherals, including B and C. For the mode R pins, I recommend defining them in this fashion, with the pin number followed by either a 1 or a 0. This is because each GPIO pin has 2 mode bits in the register, and defining them in this way allows you to keep the pairs organized. With this, let's set PA1 for a general purpose output. The datasheet tells us that setting the bit pair to 0, 1 will put the pin in output mode. We can do this with our bitwise operators. Now that the pin is in output, we can finally get to blinking it. Inside of a while loop, toggle the pin by using an XOR operator on the ODR register. For the delay, simply use a very long for loop. Like we set up earlier, you should have your ARM C compiler. I do recommend that you do have a way to run the makefile that I have provided, since it will make compilation easier. But if you're on something like Windows, you don't have to do this. Either way, let's review the makefile so that you are able to understand what it will do to automate the compilation process for us. The first line is the target. We are going to output a final elf file named out.elf. The source files are simply the names of the files that we need to compile. main.c and vectortable.c. Fill in your CPU and MCU lines as needed for your MCU. For me, I'm using the Cortex M0 Plus along with the STM32 L011F4. Please note that the MCU line is custom to my setup and it isn't needed by the compiler itself, so you can skip it if you aren't using my files. CC is your C compiler. Simply put the name of the ARM compiler that we installed earlier, ARM none iabi gcc. The C flags variable are options that we use in the compilation process. We want all errors and warnings to be reported along with debugging capability. The objects are simply the source files that we replace with .c with the .o. The next section differentiates between Windows and Linux's RM or del for deleting a file. The next couple of lines represent linking our object files together into the final alt.l file. The entry after this is how we created those object files, where the %sign represents every C file and every object file. Again, if you don't want to mess with the makefile or can't get it working, feel free to run the command on its own, like so. At this point, we can now turn our attention to the programmer. I will be using the official STM programming tool to make this a bit easier. Make sure that you select ST-Link as your programmer. Also, set your mode to under reset, and set your reset mode to hardware reset. This should make it easier to program everything, otherwise you may have to manually reset the microcontroller yourself. Afterwards, click on this button that has the arrow on it. From here, browse and find the out.l file that we created when compiling. Then, click on the Start Programming button. At this point, if everything was set up correctly, the programming should have been successful. At this point, we can see our LED blinking. I'd just like to say congratulations if you've made it this far. The setup to get to this point was not easy. At this point, we are now free to experiment with the microcontroller as normal. When using this microcontroller, you have 4 different clocking options. The HSI-16, which is an internal high-speed oscillator clock, the HSC, which is an external high-speed oscillator clock, the PLL, which gets clocked from a different clock, and the MSI, which is a multi-speed internal oscillator clock. The MSI at 2.1 MHz is used as the default clock at startup. For the remainder of this video, I want to switch to the HSI-16 internal clock. To do this, let's make a new function called initSystemClock. Also make sure to define the RCC control register and the RCC clock configuration register, along with the bits that correspond to these registers. The first thing that we'll do now is start the HSI clock with the HSI-16 on bit. Afterwards, wait on the HSI-16 ready flag to become a 1. Once it does, the HSI-16 clock is now ready for us to use. Switch the system clock by using the clock configuration register and the SW bits. After selecting your clock source, make sure to check for its validity in another while loop. You can determine that the switch was successful if your LED starts blinking at a faster rate. Luckily for our case, this clock change was actually pretty easy. However, depending on your setup and your desired frequency, you may run into some other problems. Table 43 shows us the maximum frequency that you can run your clock at depending on your voltage. Luckily, the HSI-16 works in range 1, which is the 1.8 volts range. You will also have to take a look at your flash latency. There are instructions in the datasheet if you need them, but since the default works for us, I'll just leave it at that. As usual, when testing a new microcontroller, we need to take a look at the timers. We will be looking at timer 2 specifically. It's a 16-bit timer. The features included are basically what you'd expect from a microcontroller's timer, including PWM and input capture. For the next test, we are going to set up a PWM output that requires little CPU involvement aside from the initial setup. To start, we are going to have to enable timer 2's clock in the RCC, much like we did with the GPIO clock from earlier. We are also going to have to configure the output GPIO pin to one of its alternate functions. We will use PA0 for the PWM output this time around. The first step is setting the alternate function mode in the mode R register. Next, we need to select the correct alternate function in the AFRL register. Annoyingly, the table for alternate functions is in the overview datasheet and not the reference manual. Either way, we need to set PA0 to an alternate function 2 to get it connected to timer 2 channel 1. With the GPIO out of the way, we can focus on the timer itself. The first thing that you should do is determine how much of a prescale you want. I selected 0 to skip any prescaling this time. Next, select a value for the ARR register. ARR stands for Auto Reload Register, and is basically the maximum value you want the timer to count to. I set it to 255. The prescaler, your input clock, and the ARR value all determine the output frequency. Next, change the value of CCR1 to select your duty cycle. It should be a value between 0 and your ARR value. The next register you need is the CCMR1 register. We are interested in the OC1M bits, since they determine what PWM mode we will use. Set them to 110 to get PWM mode 1. Enable the output on OC1 with the CC1E bit in your CCER register. We are almost done. Simply set the CN bit in CR1 to enable the timer, and set the UG bit in the EGR register to force all of your settings to update properly. And now, after uploading, we can see the PWM output on our oscilloscope, and it's working as expected. We can change the duty cycle by adjusting the CCR1 value in the code. Here's a 25%, a 50%, and a 75% duty cycle. Why don't we put that FTDI chip to use? The UART will allow us to serially communicate with the PC through a USB port. To start, let's take a look at the UART section of the datasheet. You should see that this peripheral comes with a lot of features and configuration. For our case, we will use a rather standard configuration of 8 bits of data, 1 start bit, 9600 baud, and 1 stop bit, and no parity bit. These settings should make it simple to set everything up properly, since they are so standard. Starting on the code, we first need to enable the UART clock in the RCC as usual. We will be using UART2 for this project. We also need to set alternate pin functions to expose our RX and TX pins. PA9 is the TX pin, and PA10 is the RX pin. They are both alternate function number 4. Now we can get to the actual UART configuration. As usual, go ahead and define the UART's registers and their bits. Let's start by setting up our baud rate. Remember, we are aiming for a standard baud rate of 9600. We need to put our special baud number into the UART BRR register. But unfortunately, we just can't put 9600 into it. Instead, the datasheet has an equation that we need to follow to find the proper value for this register. Remember from earlier how we switched to the HSI16 clock source? That means our clock will be 16 MHz. The UART div value is simply our desired baud rate. Depending on your oversampling, you may or may not also need to multiply by 2. But we will stick with oversampling by 16, so we won't need to do that. Following this equation, that gives us a value of 1667 in decimal. There are a few more things that you may wish to change depending on your requirements, such as the word length in the CR1 register. If you're reading this for the first time, you may be overwhelmed by the sheer number of options that you will come across in the register descriptions. Luckily, most of them are for other purposes, such as smart card mode. Since we are using a simple asynchronous serial communication configuration, you can ignore most of these settings. The only thing left for us to do is to enable the transmitter, the receiver, and the UART itself. Now that we've initialized the UART, we need a way to receive and transmit data to and from the peripheral. Make 2 new functions called send UART2 and receive UART2. Sending with the send function, we simply need to fill in the transmit data register with the data we'd like to send. But before we can do that, we first need to check that the TC bit in the status register to make sure that the previous data has already been sent, so that we don't accidentally overwrite the previous data. For the receive function, we need to wait for the RX and E bit to make sure that there's actually data to receive. Once it is received, we can simply return it. Now we can test the UART in our main function by waiting for a character to be received and then sending it back. On my PC, I booted up a program called Minicom, which allows me to serially communicate. As you can see, when I type a character, it is printed back to me on the screen. So the UART works as expected. Now that we've proved that we can actually use the microcontroller by setting up the other peripherals, we can finally return back to the interrupts. Let's focus specifically on the UART2 interrupts. It'd be nice to automatically echo back any sent characters without pulling the UART on a loop. You may think that we simply have to overwrite the UART2 handler, but it goes a bit deeper than that. To enable a specific interrupt handler, you have to enable it in the NVIC. Unfortunately, the important information that we need about the NVIC isn't in the reference manual, but rather the programming manual. This is the part of the tutorial where your specific STM32 microcontroller may differ greatly from what I'm doing with mine. Read everything carefully and make sure that it lines up with your specific needs. The NVIC isn't stored in the normal peripheral address space, but rather the Cortex M0 Plus peripheral address space with an offset of E100. There are 12 registers that are involved with the NVIC, and the addresses for each can be found in the programming manual once again. Pay special attention that the NVIC IPR has 8 registers involved with it. Out of all these 12 registers, the one that we are most interested in is the ISARE register, since it enables a specific interrupt. Each bit in this register enables its corresponding interrupt. Go back to the NVIC section in the reference manual to find the position value. For my microcontroller, the UART2 interrupt is at position 28. I'd recommend that you go and convert all of these positions to definitions so that you may enable interrupts that you come across. Finally, enable the interrupt by setting the bit in the NVIC ISARE register. Now that we have general UART interrupts enabled, we have to configure the UART itself to interrupt when specific events happen. I set the received interrupt bit in the CR1 register. Now the microcontroller should jump into the UART2 handler whenever data is received. Let's now write the code for the UART2 handler. I'd recommend that you check for the RxNE or the ORE bit in the status register. These are to ensure that we have the correct interrupt and that there is actually data for us to read. Afterwards, receive and manipulate the data like normal. At this point, the microcontroller can now blink normally in the main loop while still being able to interrupt and echo back any characters that I enter through the serial interface. Just as the final word and reminder about these interrupts, this NVIC system I showed in today's video is the least compatible with the other STM32 microcontrollers with different M types. Please be careful when implementing one of your own and make sure that it lines up with your specific microcontroller's datasheet. Overall, I'd say that the STM32 platform is extremely powerful and cost-effective. New projects will likely benefit from using an STM32 over something like an AVR. You get a lot more performance from these modern microcontrollers. Unfortunately, that comes with the cost that they are way more complicated. One gripe that I had with the process was having to reference 3 different datasheets just to get everything that I needed to know. Otherwise, I'd say that you should give the STM32 a shot. I especially like the open source GNU compiler that I was able to use for this project. I also took a very low-level approach when making this video. You yourself may decide to use a library like HAL, along with the Cube IDE to simplify the process. Once again, I will host links to all of the datasheets that I've used, and I will put them in the description. I'll also give you the schematic for the development board. My code will be posted in the description. Well, that should just about cover it for STM32 microcontrollers. If you've learned something new, please consider subscribing so that you can see my future videos. Also, visit my Buy Me a Coffee page, because with your support, I can keep making these videos. I'd like to take a moment to thank Mr. Dev Null, Cognizant, and Mark for being channel members. You all have made this video possible. Anyways, thanks for watching. Have a good one.